In 1977, two pioneers embarked on what might be one of the most epic feats of exploration ever undertaken. Their goal? To unravel the cosmic mysteries surrounding the solar system and our place in it. Not only did they provide us with some of the first and best imagery of our solar system's outer planets, but they continue to send us incredible new information about our universe from interstellar space, some 47 years and 24 billion kilometers later. The Voyager 1 and 2 probes are more than just instruments and circuitry. They are a symbol of humanity at its best, curious, audacious, ambitious, and resilient. Voyager didn't just capture dazzling photos of our gas giants and their moons, it captured the hearts and minds of generations back home on Earth. These are the probes that have gone the furthest that any human object has traveled. They are trailblazers and groundbreakers. It is their unique opportunity and their peril to travel beyond the reach of humanity, to capture images of things we have never seen before so close up, nor have we seen since. When I look back, I realize how little we actually knew about the solar system before Voyager, says Voyager Mission project scientist Edward Stone. We discovered things we didn't know were there to be discovered time after time. So, are you curious to see what they learned? I'm Alex McColgan, and you're watching Astrum. And in today's Supercut, we'll cover everything you might ever want to know about the Voyager missions, from the probes themselves, their grand tour, to their impending tragic finale. It's one of life's little ironies that it is not new, cutting-edge technology that is advancing our understanding most at the edge of our solar system, but old machines. They have an onboard computer with less memory than the one inside your car's key fob. To this day, they are still using 8-track magnetic tape from the 1970s, which makes them older than many of you sitting here watching this. Such is the conundrum of deep space exploration, where vast distances and extremely long travel times can mean that technology is antiquated by the time it has reached the most ambitious targets. Of course, Voyager 1 and 2 were not initially meant to travel all the way to interstellar space. They were instead built for a 5-year mission to explore Jupiter and Saturn and their larger moons, which was only possible thanks to a rare, once every 176 years planetary alignment. However, after completing all of its initial objectives on Jupiter and Saturn, the Voyager mission team added flybys of Uranus and Neptune to the probe's objectives. Later, these too were completed, so NASA announced the start of the even more ambitious Voyager interstellar mission with the purpose of exploring the outer limits of the Sun's sphere of influence and beyond. This final journey would take both probes off the ecliptic to unexplored parts of the solar system, such as the termination shock and the denser and hotter heliosheath, before finally crossing the heliopause into interstellar space. But how did these incredible machines manage to accomplish so much beyond the scope of their original mission? It all comes down to that old but incredibly effective technology. NASA scientists made a number of forward-thinking design choices that allowed the probes to far exceed their initial objectives. To put it simply, they were built different. Here's how. Let's start with one of the most consequential decisions: the fuel source. Each probe is equipped with a long-lasting radioisotope thermoelectric generator, which converts heat from the decaying plutonium-238 isotope into electric power. These generators were capable of producing 157 watts of electrical power upon takeoff, about enough to power a laptop and charge a mobile phone too. This might not sound like much, but was more than Voyager needed. While a radioisotope generator meant that power production was in constant decline, it would have in strength every 87.7 years, it would still be enough power to keep the essentials on the probes running until at least 2025. This long-term fuel capacity was no accident. You see, when the Voyagers launched in 1977, NASA faced a unique opportunity. The planets would soon be in that 1 in 176-year alignment that had last occurred during Napoleon's first reign. This rare alignment would not only allow the Voyagers to visit Neptune and Uranus with minimal course adjustment, but also give the probes a gravity assist from each of the 4 outer giants they visited, thereby increasing their effective velocity beyond what they could get from their own rocket propulsion. This idea was relatively new at the time, having been only attempted previously on NASA's Pioneer missions to Jupiter and Saturn. However, this narrow window gave NASA a strict deadline. There wasn't enough time to plan follow-up missions, and the United States Congress wouldn't earmark enough funding for a longer expedition, like the grand tour NASA first proposed. So, what did Voyager's team do? They devised a series of engineering feats to optimize the probes for a potentially longer mission, and fervently hoped that the funding would follow. Each of the Voyager probes is equipped with 11 scientific instruments. Most of them have redundancies in case of machine failure, which can be toggled on and off to conserve power. To adjust course and orientation, the probes are equipped with gyroscopes for stabilization, referencing instruments, and 16 hydrazine thrusters, including 8 backups. Backups, and good backups at that, were key to the Voyager probe's longevity. They proved to be vital, as Voyager 2's main thrusters stopped working after 37 years. Its backup thrusters had to engage after 4 decades of idleness. And guess what? They worked perfectly, highlighting the excellent engineering that went into them. The Voyagers also have custom-built onboard computers, which are antiquated by today's standards but were cutting edge in 1977. The probe's wide-angle and narrow-angle lens cameras are controlled by a computer command subsystem, which has fixed programs like fault detection and correction routines. Another key to its success lay in its computers. Each probe had a computer called the Attitude and Articulation Control Subsystem. And no, it doesn't scold the Voyagers when they get sassy. Attitude refers to the probe's orientations with respect to the Earth, without which their high-gain antennae would be unable to send or receive signals from NASA's deep space network. This is very important, as the probe's transmitters only have the wattage of a refrigerator light bulb, and at such immense distances, their radio signals become barely detectable whispers. To communicate with the Voyager team and vice versa, the probe's antennae must be facing the Earth, and the deep space network must in turn know exactly where they are. Otherwise, they would be lost, like a needle in a 287 billion kilometer haystack. Each Voyager spacecraft has a 3.7 meter antenna for real-time transmission and an 8-track digital tape recorder capable of buffering 536 megabits for future transmission, enough to store 100 photographs. While this was a huge step up from the earlier Pioneer probes, which had no onboard data storage, it's still a fraction of what the smartphone in your pocket can store today. Despite these limitations, the DTRs were built to last. Odetics, which manufactured them, claimed their DTRs could process over 4,000 kilometers of tape without taking visible wear and tear. They had to withstand the harshest environments imaginable and undergo rigors that had never before been tested. Yet, the Voyager DTRs performed without data loss or machine failure until they were finally taken offline to conserve power. Not bad for machines 12 years older than the World Wide Web. Durability was a chief concern during Voyager's planning. There are many unknowns in a mission of this magnitude. To get to Jupiter, both Voyagers would have to pass through the asteroid belt. Scientists once believed that this region would shred apart any spacecraft that tried to pass through it. However, Pioneers 10 and 11 had previously been able to pass through the asteroid belt, which emboldened Voyager's team to repeat the stunt. However, failure would have meant disaster before the probes had even reached their first target. Luckily, both probes made it through the asteroid belt unscathed, and we now know that it is mostly empty space thanks to them. Even with all these successes, and with the probes performing far better than their engineers could possibly have hoped for, as the two spacecraft traveled through the vastness between the planets, there was still at least one more hurdle to cross. What would happen to the probes in the extremely cold temperatures of interstellar space? NASA installed multiple heaters to keep the machinery operational. Nonetheless, as the probes' power waned, NASA had to turn off some of their heaters to conserve energy. When the cosmic ray detector's heater was turned off 2 years ago, its temperature plummeted by 70 degrees Celsius. Needless to say, sending a repair team 23 billion kilometers into space isn't an option. So everyone thought the instrument would break, but it continued to run smoothly. The fact that the probes have operated so well for 45 years is a testament to their resilience and engineering. But with all this technology, what did they see? Let's go back to the beginning and follow the path they blazed across our solar system. On August 20th, 1977, NASA launched the Voyager 2 space probe from Cape Canaveral, Florida. Its partner in crime, Voyager 1, was launched 2 weeks later on September 5th, 1977. Even though both probes were Jupiter-bound, Voyager 1 was set on a shorter, faster trajectory, so taking off second made sense. It overtook Voyager 2 on December 15th, 1977, and exited the asteroid belt first. Together, this dynamic duo was set to take a dazzling parade of pictures that were absolutely revolutionary at the time. But don't take my word for it. Let's jump in and you'll see for yourself. 13 days after launch, Voyager 1 sent this photo back to Earth, the first of tens of thousands it would send back over the next 5 years, taken 11.6 million kilometers from Earth. It's a sentimental place to start our journey. It might remind you of the Earthrise photo taken by the Apollo 11 crew from the moon just 8 years prior. We can see our blue marble and its moon in the distance. I don't know about you, but I find this photo so hauntingly beautiful, especially knowing how far this probe has traveled and how much it's seen since then. But we've got a long way to go, so let's move on. It would be almost 2 years before Voyager 1 finally makes its approach to its first target, Jupiter. Not bad, considering it's 714 million kilometers away. Voyager 1 arrived first on March 5th, 1979. You see, it travels at 17 kilometers per second, 2 kilometers per second faster than Voyager 2, who, despite leaving Earth first, arrived 4 months later on July 9th, 1979. This is because the trajectory Voyager 1 took allowed it to gain more speed relative to the Sun. Now, Voyager 1 was not the first spacecraft to encounter Jupiter. That was Pioneer 10, 7 years prior in 1972. And while the Pioneer mission certainly provided great scientific insights, it didn't quite grab the imagination of the public. But sending back stunning images like this, Voyager certainly did. This is Jupiter in all its glory. It's kind of hard to accept that these are actual photos and not paintings or some AI-generated image. If you look closely, you can spot two of its moons, Io on the left and Europa, the beige one on the right, but more about them later. Lucky for us, Voyager 1 even recorded its approach to the great gas giant. It took photos at regular intervals every 10 hours, or one Jupiter day. This means the planet is in the same point of its rotation in all the photos. The 66 photos were spliced together to create this time-lapse movie, spanning Voyager 1's approach to Jupiter from January 6th to February 3rd, 1979, covering a distance of 27 million kilometers. I personally can't decide if it is incredible or terrifying, but let's get a closer look and see what surprises this planet is hiding. Something that immediately stunned scientists was Jupiter's atmosphere. They expected to see east-west and west-east winds in Jupiter's different atmospheric zones, but what caught them by surprise was the amount of turbulence, plumes, and rotational movement, which are super clear in this image. You can immediately see how dynamic the atmosphere over Jupiter is. Scientists had already suspected Jupiter's most notable characteristic, its great red spot, might be a counterclockwise rotating formation. Not only did Voyager data confirm this, it also showed a surprising amount of similar phenomena in other parts of the atmosphere. The white spot you see below the great red spot is one example of these surprise storms. Turns out Jupiter's atmosphere is littered with them, and we had no idea. When we think rings, we think Saturn. But thanks to Pioneer data, scientists have long suspected that the same is true for Jupiter. Voyager data not only confirmed the existence of 4 Jovian rings, it was also the first to image them. This picture taken as Voyager leaves, Jupiter highlights the rings beautifully, as that glowing orange line protruding from the planet. Before we leave Jupiter and continue our journey, I did promise we would come back to its moons, Io and Europa. Possibly the biggest shock from the Voyager expedition is the discovery of volcanic activity on Jupiter's moon, Io. Prior to Voyager, geologists thought Io would be covered with large impact craters like our own moon. While they did find circular markings on Io's surface, they didn't appear to be from craters. The dark spots you see indicate the presence of volcanic hotspots and lava lakes. This photo shows lava flow from less than 1 million years ago, which is incredibly recent and totally unexpected. We now know Io as the most geologically active site in the solar system. At the time of these images being taken, it would have been incredible to capture Io mid-eruption. Imagine expecting to see a moon similar to ours and then stumbling upon a site like this. These blue explosions on the surface of Io shot material and gas 100 kilometers into space. The volcanoes are incredibly active, going off relentlessly every few hours, treating Voyager to several jaw-dropping photos. The next moon out from Io is Europa, and it could not be more different. An icy world. Voyager 1 was the first to show us that Europa is covered by curious scratch markings. Scientists suppose them to be some type of ice fracture patterns on Europa's surface. It was also Voyager data that first suggested there might be a swirling ocean lurking under the ice. Today, we know of 95 moons orbiting Jupiter. However, prior to 1979, that number was 13. Voyager discovered 3 new satellites, Thebe, Metis, and Adrastea, bringing the total to 16 moons by the early 80s. Sadly, we don't have any pictures of them from 1979, though they have been imaged since. The next stop on Voyager's grand tour was Saturn. After 21 months of travel, Voyager 1 arrived on approach to the ringed planet in November 1980, closely followed by its companion 9 months later in August 1981. Like I said before, you think rings, you think Saturn. So let's start there. Prior to Voyager's mission, Saturn was believed to have just 5 major rings. However, Voyager 1 showed us that these rings are actually made up of hundreds of thin ringlets. This was the closest flyby any probe had undertaken back then, hence the greater detail and learnings. Voyager discovered a ring too, the G ring, and also provided key details about the F ring discovered by Pioneer 2 1 year prior in 1979. Voyager 1 showed us that the F ring is kinked and multi-stranded in nature. It also identified 2 shepherd moons within the F ring, Prometheus and Pandora. This was big news because this discovery confirmed scientists' theories that shepherding moons exist around narrow rings to keep ring material in line. Voyager also introduced us to some ghostly features on Saturn's B rings. They appear scattered around the rings in this photo and are said to resemble broad spokes in a wheel. They seem innocent, but they actually caused quite the stir in the scientific community for a while. You see, up until 1980, we thought that Saturn's rings were caused exclusively by gravitational forces. That's all well and good, except these spokes completely fly in the face of that theory. Their existence is not consistent with gravitational orbital mechanics. We still don't know what causes them, but the leading theory involves electrostatic repulsion separating very small dust particles from the main surface of the ring. Sadly, as much as data from Voyager taught us about Saturn's rings, it also taught us that Saturn is losing its rings. Gravity is pulling the rings into the planet, turning them into a kind of dusty rain of ice particles. According to NASA, this could cause Saturn's rings to disappear in 300 million years. Voyager's trip to Saturn raised so many questions that a dedicated mission was mounted in the 90s to exclusively study the ringed planet. Cassini probe launched in 1997 and orbited Saturn for 13 years. You can check out a video of mine on what it found here. But we aren't leaving Saturn territory yet. Voyager provided some decisive breakthroughs regarding the planet's moons. We already knew of 14 moons, but Voyager showed us 3 more, bringing the total number at the time up to 17 moons. Let's see what we can learn from Titan and Enceladus. Pioneer 11 was the first probe to image Titan, Saturn's largest moon, and the data it gathered captured the interest of researchers. So, Voyager was sent to follow up. It found that Titan had a thick, nitrogen-rich atmosphere, the first and only encounter of such an atmosphere beyond our home planet. Enceladus also turned out to be exceptionally quirky. Take a look at this photo. Enceladus is visible out in the distance, with Saturn in the foreground. Now, I know it's tricky to see, but that moon is erupting. Enceladus spews out 300 kilos of water vapor up to 10,000 kilometers above its surface, 20 times its own diameter. As it orbits Saturn, the frequent plumes of water vapor that erupt leave behind a donut-shaped cloud that feeds one of Saturn's icy rings. This data was suggested by Voyager data, but it wasn't until we flew Cassini out there that we could confirm it to be true. Further geological data and imaging shows that Enceladus's terrains are an unexpected mixture of old and new. The left side, which appears smooth, is the newer side, and the right side with the densely packed impact craters is the older side. This suggests Enceladus is a very geologically active moon, which it wasn't previously thought to be. Before we make our way to the wonky world of Uranus, we have to say goodbye to Voyager 1. After its flyby of Titan and Saturn's rings, its path was bent upward out of the ecliptic plane. From here, the probe headed straight for interstellar space. Of course, it would be another 32 years before it would reach that. But not to worry, Voyager 2 took a slingshot around Saturn instead, to propel it onto Uranus and Neptune. These would be the first and only flybys of the planets in human history. 5 years after arriving at Saturn, NASA's Voyager 2 arrived on approach to Uranus in January 1986. At its closest, the probe came within 81,500 kilometers of Uranus's cloud tops. Voyager 2 revealed an absence of visible cloud features in Uranus's atmosphere. Unlike Jupiter and Saturn, Uranus displayed a serene, featureless cloud deck, challenging scientists' preconceptions about the atmospheric dynamics of gas giants. The false color image on the right brings out the subtle differences in the atmosphere of the polar regions, which are tilted on a 98-degree axis. But it was another tilt that stunned Voyager scientists. It was previously unknown whether Uranus had a magnetic field, but Voyager data showed us that not only does Uranus indeed have a magnetic field, it is also tilted at an astonishing 59 degrees. That means its magnetic and rotational poles are not at all in the same place. Until then, it was thought that these poles were always aligned. It certainly is here on Earth. Our magnetic and rotational poles are only shifted by 12 degrees. This stark deviation found on Uranus defied conventional planetary magnetic field models and forced scientists to rethink their assumptions. One side effect of this misalignment of poles is that as the planet spins, its magnetosphere, the space carved out by its magnetic field, wobbles like a poorly thrown football. Scientists still don't know how to model it, but it might look a little something like this. Voyager 2's observations unveiled more details about the known rings of Uranus and discovered 2 more. It is the first to capture images of these dark rings, like its outermost ring visible in this photo. The rings are composed of fine dust particles. Voyager 2 also discovered 2 shepherd moons orbiting one of the newly discovered rings, similar to its findings with Saturn's to the F ring. Here, they can be seen from 4 million kilometers in a photo from January 21st, 1986. This mission significantly increased the known count of Uranian moons. Prior to Voyager 2, we only knew about 5 moons orbiting Uranus. Voyager 2 sent us the first ever images of these moons, which you'll see in a second, but it also discovered 11 more moons, bringing the total to 16 moons. Voyager's discovery provided valuable data on their new moon sizes, compositions, and orbital characteristics. Today, the number of known moons stands at 27. Okay, back to Uranus's 5 OG moons. They all appear to be ice rock conglomerates, similar to the moons of Saturn. Oberon and Umbriel pictured here on January 24th, 1986, are riddled with impact craters. They seem to have little geologic activity, judging by their old and dark surfaces. Titania, which sits between those two, fourth furthest from Uranus, is marked by huge fault systems and canyons, indicating some degree of geologic and probably tectonic activity in its history. Ariel has the brightest and possibly youngest surface of all the Uranian moons. This photo, taken from just 129,000 kilometers, suggests Ariel underwent geologic activity that led to many fault valleys and extensive flows of icy material at some point in its history. Miranda is the closest of the five to the planet, second only in proximity to Puck, the little rocky satellite discovered by Voyager in 1985, and had the most surprising findings. Voyager flew by Miranda on January 4th, 1986, at a distance of just 30,000 kilometers. This small moon turned out to be a captivating puzzle of geological dynamism, shaped by a volatile history. Voyager 2 identified traces of internal melting and sporadic upwelling of icy material, manifesting in extensive canyon-like faults plunging to depths of up to 20 kilometers. The lunar canvas is further adorned with oval, racetrack-shaped features etched like cosmic scratches. Voyager also saw terraced regions, where a mosaic of old and young, bright and dark, and heavily and lightly cratered terrains coexist. The chevron-like characteristic seen here suggests Miranda's original surface was pulled apart and the fragments forcibly reaggregated back together. 3 weeks later, on January 25th, 1986, Voyager 2 departed Uranus and snapped this wonderful goodbye shot from 1 million kilometers as it set off to its final planetary target, Neptune. After 3 years of travel at a speed of 54,000 kilometers per hour, Neptune finally came into view. Voyager 2 approached the furthest planet in our solar system on August 25th, 1989, just over 12 years since it took off from Earth. It produced the first up-close images we ever received of the giant blue planet, passing only 5,000 kilometers above its north pole, the closest of any flybys. Hydrogen was found to be the most common element in Neptune's atmosphere, although the high abundance of methane is what gives the planet its blue appearance. Voyager 2 measured extraordinary wind speeds in Neptune's atmosphere, with the equatorial winds blowing at speeds reaching almost 1,100 kilometers per hour. These remarkable speeds were yet another surprise, and highlighted just how dynamic and ferocious Neptune's weather systems are. Scientists also discovered a massive storm on Neptune, aptly named the Great Dark Spot. This turbulent storm was seen to be rotating counterclockwise, just like the Great Red Spot on Jupiter, and exhibited winds reaching up to 2,400 kilometers per hour, the strongest recorded in the solar system. One NASA analyst, Ken Bollinger, commented on the findings in 1989. Voyager 2 also imaged Neptune's rings for the first time. Up until 1986, scientists suspected the planet might have rings, but couldn't be certain. Intriguingly, the spacecraft identified several partial ring structures, or ring arcs, within Neptune's ring system. These arcs raised questions about the mechanisms responsible for their formation and stability, since they mainly consisted of incomplete and dusty rings. A trip to Neptune wouldn't be complete without a quick stopover at its largest moon, Triton. The coldest known planetary body in the solar system, Triton turned out to have a fractured surface complete with erupting geysers and a pinkish nitrogen ice cap over its southern pole. Scientists also identified dark plumes, which could indicate the possibility of ice volcanoes. Voyager 2 also discovered 6 new moons orbiting Neptune. As Voyager 2 turned around to snap one last look at Neptune and Triton, it had officially completed its grand tour. Neptune's gravity bent its path downward out of the ecliptic plane. From here, it continued its voyage into interstellar space, just like its counterpart Voyager 1 had done 9 years before. Speaking of Voyager 1, let's see where it's ended up since we last checked in 1980. 1 year after Voyager 2 finished up with Neptune, Voyager 1 was already about 6 billion kilometers away. In order to conserve power for the long journey into interstellar space, scientists were going to switch off its cameras forever. However, on the advice of Carl Sagan, the team decided to turn the camera around for one final picture, a look back at home and how far we had come. And so, on February 14th, 1990, Voyager 1 took the most remote selfie in history from 6 billion kilometers away. The result? The infamous pale blue dot photo. Carl Sagan later wrote movingly about what that image meant, reflecting on how small and precious our world looks from such a distance, and how it should inspire humility and care for one another and for the only home we have. This sentiment rings with as much power today as it did decades ago. But what came next? What did the Voyager probes see and do in interstellar space? In 1981, Voyager 1 escaped the ecliptic, which is the Earth's plane of orbit around the Sun, heading 35 degrees to the north. Voyager 2 later went under the ecliptic, heading 48 degrees to the south. However, this was barely the start of the Voyager's journeys. To reach interstellar space, the probes would have to traverse the termination shock, a region in which hypersonic solar winds run into fierce resistance from the interstellar wind. Beyond the termination shock, the Voyagers would encounter the heliosheath, where slowing solar winds pile up, becoming denser and hotter, followed by the heliopause, the final boundary between the heliosphere and interstellar space. But in spite of what you may think, the start of the interstellar medium doesn't actually mark the end of our solar system. Indeed, it will be another 300 years until Voyager 1 reaches the Oort cloud, the vast region of billions of icy planetesimals that surrounds our solar system like a bubble, and another 30,000 years until it exits the cloud, leaving our solar system forever. When the Voyagers traveled through the heliosheath, they made an incredible discovery. Because the sun's magnetic field spins in opposite directions on its north and south poles, the spin creates a ripple where they meet called the heliospheric current sheet, sort of like the rings created by dropping a stone in water. However, when this sheet reaches the termination shock, it compresses, as though the ripples were hitting the edge of a pool. The Voyager probes discovered that after the termination shock, these stacked up ripples form magnetic bubbles. This means the boundary of the heliosheath is not as smooth and clear-cut as scientists thought. Instead, it is a fluctuating and magnetically bubbly environment. This messy finding has prompted a complete revision of our model of the heliosheath. On July 25, 2012, the Voyager 1 space probe became the first man-made object to leave the sun's heliosphere and enter interstellar space. It was traveling at an incredible speed of 540 million kilometers per year, or 3.6 astronomical units, an astronomical unit being the distance between Earth and the sun. The distance at which Voyager 1 crossed the heliopause was about 120 astronomical units from the sun, which itself was a revelation. It was unknown where exactly the heliopause occurred. Funnily enough, some early models put it as close as Jupiter, and others much farther. Remember, the heliopause is the boundary where the sun's solar wind is stopped by its collision with the interstellar medium, kind of like the crashing of two powerful bodies of water against each other. Solar wind is the steady stream of charged particles, such as electrons, protons, and alpha particles, that come from the sun's outer layer. The interstellar medium, by contrast, consists of charged particles, gases, and cosmic dust left over from the Big Bang and other ancient supernovae. When these charged streams hit each other, they change course and form a region of equilibrium called the heliopause boundary. At first, NASA wasn't sure if Voyager 1 had truly crossed the heliopause and entered interstellar space. As models predicted, the probe's plasma wave detector found a massive increase in plasma density, 80 times what it had registered in the outer heliosheath, and a spike in galactic cosmic rays. But something strange didn't happen that left scientists baffled. After crossing the heliopause, Voyager 1 detected no change in the ambient magnetic field. Why was that so surprising? Well, theoretical models assumed that the ambient magnetic orientation would change in a region dominated by the magnetic fields of other stars. But remarkably, Voyager 1 detected no discernible change in the ambient magnetism. NASA was so confused that they waited nearly a year before announcing that Voyager 1 had, in fact, entered interstellar space. On November 5, 2018, Voyager 2, traveling at the slightly slower speed of 490 million kilometers, or 3.3 astronomical units per year, joined Voyager 1 in becoming the second man-made object to enter interstellar space. The crossing also occurred 120 astronomical units from the Sun, and like the Voyager 1 6 years earlier, the probe detected no change in the ambient magnetic field. But something else surprised scientists. You see, the Sun goes through 11-year solar cycles, during which its activity waxes and wanes. Voyager 2's crossing occurred at a time when solar winds were peaking. Models predicted that the size of the heliosphere would fluctuate with the solar cycle, meaning it would have been expanding when Voyager 2 made its crossing. Yet Voyager 2 crossed the heliopause at exactly the same distance Voyager 1 had 6 years prior, meaning our models were wrong. Like the magnetometer finding, this demonstrated the value of testing theoretical models with field data. We now suspect that the boundary between the heliosphere and interstellar medium is much more twisted and filled with fluctuations than prior models proposed. One leading idea is that our Sun emerged billions of years ago from a hot and heavily ionized region following the explosion of one or more supernovae, and that magnetic turbulence persists to this day near the heliopause. If so, the probes will likely encounter a different magnetic orientation as they travel farther away, but their instruments will probably be long dark by that time. After all, the probes are already starting to fail. In early May 2022, Voyager 1's signal went strange. Imagine you are a NASA scientist. You arrive at your computer for the day and begin looking through the Voyager 1 telemetry data. Voyager 1 sends back status updates about its systems, letting you know whether everything is functioning normally. It takes 22 hours now for a signal to reach Earth from Voyager 1, so communication is a little slow between you and the craft you're overseeing. Currently, it is more like sending letters than texts. However, today, something is wrong. The information it has sent you is gobbledygook. Instead of precise data explaining exactly what Voyager 1's thrusters are doing and what orientation it believes itself to be at, you get long strings of zeros or 377s. The information does not make sense. It suggests that Voyager is doing things and pointing directions that cannot be. You quickly check your computer again. Yes, you did just receive a signal from Voyager 1, so its antenna must be pointing towards you, the same as it always has. It cannot be pointing in the strange directions it is claiming, or you would not be getting a signal at all. And not only are you receiving the signal, but it's at the exact same strength too, so it has definitely not changed its direction. And ping, onto your computer comes Voyager 1's latest science data. Strangely enough, this is all normal. While over the years, Voyager 1 has had to turn off 5 of its 11 pieces of scientific equipment, and a further 2 have stopped working due to general degradation, the remaining 4 continue to take readings about the interstellar medium, magnetic fields, and cosmic rays. Nothing here is garbled in any way. You check its other systems. Voyager 1's power supplies are a little low, but that's to be expected. The plutonium oxide that fills its 3 generators have a half-life of 87 years, but Voyager 1 has been traveling for 45 now. It is no wonder the efficiency has started to decline. In fact, the experts believe that Voyager 1 will not last past 2025. But that is some time away. It does not explain what is happening now. After checking its other systems, it is just one that is behaving strangely. The AACS, the Attitude Articulation and Control System. This computer is one of 3 on Voyager 1, and remember, its job is to make sure the spacecraft's large 3UM antennae continues to point towards Earth. This AACS has stopped sending coherent data. You lean back, puzzled. The situation is not as bad as you might have thought, but it is troubling. It's kind of like receiving post from a postman who says hello to you every morning, only for some reason he starts speaking another language one day. The packages he delivers are still the same, and they've arrived at the same address. It's just the words the man speaks make no sense to you anymore. To further compound the strangeness, Voyager 1 doesn't think that anything is wrong with it at all. The spacecraft comes equipped with emergency safe mode settings that it can go into if it detects that anything is not working the way it ought to be. Essentially, these involve powering down until scientists can figure out what's wrong with it, and these have not activated. So Voyager 1 believes that all its systems are working the way they should be. The data is given, the scene is set. This was the question that NASA engineers faced in mid-2022. A single fault like this might not seem like a big deal, but it hints at something potentially wrong with further systems. And if that is true, it might spell an end to the whole mission. Voyager 1 is, by now, 23.8 billion kilometers away from you. Your solution will have to be made via deduction, alongside careful 22-hour each-way questions and answers with the faulty spacecraft. By evaluating the rest of the systems and finding them normal, you can rule out some of the more unusual explanations. No, this probably is not the work of aliens trying to mess with you. Although NASA scientists were open to the idea of the Voyager probes maybe one day being picked up by alien life, as evidenced by the golden discs installed on the probes filled with messages about us for aliens to read if ever they stumbled across it, this was more a symbolic gesture. Besides, it seems that this would be a strange way for aliens to communicate with us. And no, the laws of physics have probably not broken down. Voyager 1 has not entered a wormhole that is skewing where it thinks it is while still somehow getting the signal back to you. Given that the scientific data all appears to be providing normal readouts, it's much more likely that the problem lies with the AACS itself. For 4 months, scientists and engineers gently prod and examine Voyager 1, testing theory after theory and trying to come up with a solution that fixes things without causing any further damage in the process. They could switch over to a backup system. It would not be the first time they'd started using a new computer on Voyager 1 after the old one stopped working. Voyager 1 is built with redundancies. This isn't even the first AACS computer that's been used. A previous one became defective a while ago. They also contemplate just leaving things be. After all, the science data is still coming in. Would it be the end of the world if Voyager 1 simply carried on speaking garbled messages? Perhaps this could simply be the new normal, except it implies that a deeper problem is being overlooked. Can you figure out what was going wrong? If you can, perhaps NASA should look to hiring you. It turns out that in the intense, radiation-filled environment of interstellar space, something had made Voyager decide to start using that older, broken AACS computer to send data back to Earth. Because of the faults in this computer, the data had become corrupted, resulting in the strange numbers. So actually, in this case, the fix was easy. All NASA had to do to fix it was to ask Voyager to start using the right computer again. Once Voyager 1 did that, the problem was resolved. Well, I say easy, and I say resolved. It still took a couple of months for Voyager 1 to start behaving normally again. And even then, in November 2023, another of Voyager's onboard computers, this time the flight data subsystem, underwent a similar problem and became unable to send home usable science and engineering data. It took until June 2024 until that particular problem was fully resolved. Voyager 1 is an old ship now. As it continues to travel through interstellar space, it may encounter more and more faults. In July 2023, a routine series of commands sent to Voyager 2 caused the probe to orient its antennae 2 degrees away from Earth. The seemingly small divergence was enough that, over the massive distances involved, NASA completely lost the ability to talk to Voyager 2, or hear back from the probe. It was only through sending out an interstellar shout from the Deep Space Network facility in Canberra, Australia, that a signal was able to be sent to Voyager 2, telling it to reorient itself back towards Earth. The 37 hours of waiting for the shout to arrive, and for the probe to signal back that it had followed the command must have been tense for NASA personnel. The probe could have been lost forever. One way or another, it's inevitable that the Voyager probes will stop transmitting back to Earth. Whether through error or malfunction, or simply running out of power, the end is unavoidable, and the curtain will fall on this incredible mission. But even then, the twin probes are just beginning their cosmic journeys. In 40,000 years, Voyager 1 will likely drift toward a star in the Camelopardalis constellation, while Voyager 2 will pass 1.7 light-years from the star Ross 248. In 296,000 years, it will pass 4.3 light-years from Sirius. These small, intrepid probes will likely outlast the Earth itself as they continue their solitary wanderings across the Milky Way. And if by chance they encounter intelligent life in one of the far reaches of our galaxy, they will be a testament to mankind's ingenuity and resilience. On each of the probes was a message to the stars, golden audiovisual discs called the Golden Record, carrying photographs of Earth and its many life forms, the sounds of whales and of babies crying, music from many cultures, and greetings in 55 languages. They would offer a distant stranger a glimpse of who we are and what life on Earth is like. As for us, we must say goodbye to these old, familiar friends and continue our own lives here on Earth. Hopefully, the Voyager mission will not be our last brush with the stars, but only the beginning.